Hi everyone, welcome back to Chem 121. Today we have more Chapter 2. Chapter 2 is the math chapter, so we're going to be doing a little bit of addition and subtraction and all those good things that you learned once long ago and, dare we say, you learned incorrectly for science. We're going to show you the correct way to do addition and subtraction and multiplication and division in the sciences so that you can get the same answer every time based on the measurements and tools that you have available. But before we do that, let's talk a little bit about the announcements that are at the bottom of the page here. So we finished chapter number 1 last week, so I put the quiz up. That quiz will be due on Wednesday. Remember that all the due dates on the bottom of the announcements that you're going to see are soft deadlines, which means that you still have a 24-hour period after those due dates to turn it in with no penalty. But if you miss that second hard deadline, then that's where you start to lose all your points. That would be bad. So don't do that. Make sure you get your assignment in on time. Also, after we've done the math part, I'm going to talk about lab number 1. So I put the due date on the bottom there for lab number 1. That worksheet's going to be due on Wednesday, not this week, but the following week, which is week 3. So that's the 21st of April. And again, we'll talk a little bit about that in just a moment because we're going to do this section and the next section, and then I'm going to show you that lab. So probably after the break today, we'll get to that. All right, let's get started once I'm actually in the right window here. There we go, okay. Now, when you are measuring something, and so that something could be like how many tablets you have to give to this patient and have them take for medication. Or it might be how many milliliters of medicine do you need to pour into this little sippy cup? You know, the little tiny plastic cups that are like upside down on top of the medicine bottle, and you pour it into that and then you drink from it. Like how high do you have to fill that? Both of those are measurements. Now, in one case, in the number of pills, you can't really have error. For example, if I draw out 5 pills here, as long as you do this counting process correctly, you're not going to accidentally give somebody the wrong number of pills with a margin of error that isn't like a whole pill. Like, you can't give somebody 5.1 pills if they come in discrete things, right? Now, the reason that you won't make a mistake in making this measurement is because we're just counting, right? Everybody can count to 5. I mean, I am making an assumption that we're not going to miscount and that this is a simple task that we can all do. And I realize that, especially for me, that is not always true. But let's assume that we know how to count. If I'm counting something, and I'm counting correctly, there is no chance for error. What that means is my answer is going to be exactly 5. It's not going to be 4.999. It's not going to be 5.01. It's going to be 5. And so we're going to define something that has no error at all, an exact number. When I say no, I mean absolutely no error. Now, with one of those little cup things that have the little lines on the side like this, maybe this line says 10 milliliters. Even if you do the correct technique and you fill it to the right volume, I don't know what this black ichor is that I'm feeding something. Maybe it's like Jägermeister. That cures all your ills, right? Or cough syrup that's just like really thick and concentrated or whatever. But even if you measure this correctly, we're measuring it on a scale. I misspelled scale there because I don't know how to spell. So let me get rid of that. There we go. You're always going to have some error. Because no matter how good you are at filling this cup, you're not going to land exactly on the line. You're always going to be a little bit higher or a little bit lower, right? You could always get closer. And at some point, you just stop because you're just so close to the line. So this cup will not hold exactly 10 milliliters. It will hold 9.98 or maybe 10.03 or maybe 10.00000001 milliliters based on just what you pour in there. The odds of you landing on exactly 10 milliliters are infinitely small because you'd have to get it down to the atom, right? And that's not possible. So we're going to call a number that is measured on a scale and has some error in it an inexact number. Okay, so these are the two types of numbers that we're going to be working with. If you're just counting something, you can be exact because you're not going to be off by 0.1 or something from counting. But if you're measuring something, you are always going to be off by some amount. You can never get it exactly right. So we're going to differentiate between those two, exact and inexact. Now, it turns out that there is another way to get an exact number. I don't know how to spell today. Wow. I'm like trying to spell phonetically in my head. Definitions. I was going to put S-H-U-N or something. If you have a definition, for example, 1 foot equals 12 inches. We've defined this measurement to be true. We just said so. Like, how many inches are in a foot? 12. Why? Because we said so. Definitions are considered to be exact also. So if you have exactly 1 foot, you would also have exactly 12 inches, even though you could be measuring the inches on the foot scale. All other numbers that use scales or balances or tools to be measured are going to be inexact. So be mindful of the situation that you're looking at when you are doing the measurement. Now, I could count the number of people watching this video right now on YouTube. If I go to here, and I can show you this actually, just in case you were curious. So this is what it looks like. This is what I see from behind the scenes here. Well, I mean, that is what I see, but it's that's a little small. So hold on. Well, it's not small. It's just it is fit incorrectly on the screen here. So you could see. There we go. So you could see right here, in this spot right here, this is the number of people that are watching right now. 10 is actually more than I expected to for week 2, since I didn't give you an announcement. And what the system is doing is it's counting the number of connections that have been made, but it doesn't have an error associated with this. So there's not 9.9 people connected or 11.1 or whatever it is. There's just 10. There are 10 inbound connections. That has been counted by the server. Now someone is logged off because they think it's boring, which I can't blame you. We're talking about number theory here. So this is a counted number, and thus you can trust it to be exact. There are exactly 9 people watching. But if I was doing something like trying to measure the... let me think of... I was trying to think of one that was related to the YouTube video on the screen, but I can't find one. If I go to, like, say, my weight, for instance, if I tried to measure my weight, if I tried to estimate that myself, there would obviously be some error there because I don't know. But even if I stood on a scale, my weight would fall between some marks here. So maybe my weight is this on the scale, and so I would have to estimate that. And then I had to make a guess as to what that number was. It might be like 100.1, or it might be 100.4, or whatever. Since we're using a ruler here to make a measurement, we're going to look at an inexact number. And what that means is that you're going to get a number, and there might be some error associated with it. And the way that we're going to test that is that when you think you know how to measure this object, write in the chat the number of centimeters that you think this is. So this is in centimeters, and it goes all the way back to 0, and this object is flush with the very end of it. Okay? So write in the chat what you think this measurement is in centimeters. And then we're going to look at all of your numbers. In fact, what I'm going to do is I'm going to turn off the chat real quick. Boop, you can't see it. I mean, obviously you can see it where you're typing in the chat, but type in your number and then like look away or something like that. And then I'm going to put all of the numbers back on the screen that everybody wrote down, and we're going to see something interesting. Okay, so put your guess in, and I'll give you about a minute and a half just to get your guess registered. Okay. What I'm actually going to do is I'm going to hit this button. We're just going to make it really big. Oh, now you can see the chat. Oh, boo. Well, we'll just hide that again. Boop. There you go. Does that help you any to make your measurement? Hopefully, because it's a lot bigger now. All right, so now what you'll notice is that when I open the chat back up again, boop, you'll notice that everybody, I got to turn it back on over here, everybody has more or less guessed differently, right? We've got all sorts of different numbers there. Now, a lot of those should be similar, but for various reasons, different people wrote different numbers. So that tells us two things. One, there is error associated with the measurement because we get different numbers for our results. And two, we need a consistent way because not everybody's reporting a similar answer, right? All right. So what I'm going to do is we're going to go back to this screen. I need to make this small again here. And then what we're going to do is we're going to write out a set of rules on how to measure anything. Not in pink, though, because that's a hard color to see. There we go. All right. And then we'll take this up here and we'll make it... Oops. I held down the wrong button. There we go. All right. We'll do our work on that while we're doing this. So step number one for how to measure anything is to find the two marks the object falls between. I don't know what happened there. Hold on. Between. All right, so on our ruler here, if I go look at which marks the object falls between, here's my object, so I'm going to draw it straight down onto the thing. What are the marks it falls between? So that's this one and that one. And I'm going to indicate what those numbers are. So this is 11.1, 2, 3, 4, 5, 6. And this is 11.7. Because that's what those tiny marks mean. That's every 0.1, right? And then the slightly longer one is 0.5, just so that you don't have to lose count every time you're trying to count. All right, so we found the marks. Cool. That's easy enough. We can always do that. Step 2 is to write the smaller of the two marks. Okay. And what I should say is write the value of In fact, due to the marvel of copy and paste, what I can do is this. Ooh, there you go. It's cheating, but that's okay. Oops, I hit the wrong button. Write the value of, oops, the smaller of the two marks. There we go. So now what we're going to do is we're going to write down the value of the smaller of the two marks. But that isn't the last step, so hold on. So the smaller of the two marks is this one, so I'm going to write that down. And then step 3 is estimate the next one digit. And so what that means is that we need to estimate the next one digit. And so I need to put a number in this spot here. And that number needs to be based off of what we see in our drawing here. So you could see here's where our mark goes, right there. So I had to estimate the next number. Would it make sense for me to estimate that the next number is 0? Well, not really, because if it was 0, that our object would land right on the 11.6 line, right? It'd land right here, but it clearly doesn't. It's more in the middle. So 0, not a good number to guess. We're not going to guess it. Does it make sense that the next number we guess should be 9? Well, if it did, it would fall way over here next to the 11.7 line, but just before it, right? So that number doesn't make sense either. Now, you could apply this logic to a bunch of numbers. You could say, oh, I wouldn't guess 1 or 2 or 8 or 7. But as you start getting closer to the middle, you start to get some numbers that it seems like it would be okay to guess, right? So 5 is a good guess. But you know what's also a good guess? How about 4? Could I guess 4? Yeah, it's plausible that this could be 4. It's hard to see, right? Could it be 6? Yeah, that's probably good too. So you actually get a range of answers that are okay. I think anywhere within here would be all right. You can't see the numbers that I wrote because I went off of what I was capturing there. There we go. So the red numbers are going to be based off of... So these come from the device. In this case, that's the ruler. And then the last digit that we add in there, this is our one estimated digit. Okay, that's how you measure. So the correct answer would be something in this box. But you could see that many of these answers are acceptable. You can't see what I wrote there. Sorry. And because there are many acceptable answers and not just one acceptable answer, that shows that there is some error associated with our measurement. Because if there was no error, we would get the same answer every time. Even though we're doing it correctly, there will always be error. So that's how we measure anything in this class. Whenever you have a scale, you're going to be measuring something against a scale by following this process. First, you want to figure out what the marks are that your object falls between. Then you want to write the value of the smaller of the two marks. That's going to be the numbers that come from your device. And then you're going to estimate the next one digit based on what you've written down and what you observe on the scale. All right, so let me clear this. You'll see that my slide walks through this. This is what I wrote on the slide. But again, you can have a variety of answers here because it's impossible for us to accurately assess that second decimal place that we are estimating to 100% certainty. It's not possible. We can't do that. All right. Here's the same process. I don't know why I always do it in 3 steps, and then when I show you, it's always in 2. I for some reason that this step is just steps 1 and 2 that I wrote down, and I always think that I want to break it into 2 steps, but that's whatever. It works the same way. If you want to do it this way with just 2 steps, then you're good. All right, so the next thing that I want you to do is I'm going to give you these 2 rulers. And so what I'm going to do first is put ruler A on the board. Oops. I gotta do it this way. All right. I'm going to put ruler A on the screen, and I want you to use the rules to measure anything to tell me the correct measurement for ruler A. And then in a second, we're going to do ruler B. So write down your measurement for ruler A. Follow the steps on how to measure anything that are shown on the screen below ruler A, and report your answer in the chat. We'll go over them together in just a second. All right, so now that you've got your answers for ruler A, let's follow the rules that we just did. And hopefully it will show up on the screen here. Great, you can see my pen. Okay, so I'm going to look at the marks that this falls between. So it falls between 4 and 5. I'm going to write down the smaller of those 2 marks. And then I'm going to guess the next 1 digit. Well, it's kind of in the middle right here, right? So I'm going to guess the next digit to be 5. Now, you could guess 4 or 6, and that would be fine. It's all based on how good you are at estimating. Okay. Now we're going to do ruler B, which probably ends over there. We'll bring it over here. There's ruler B. So now, based on what you see on ruler B, do the same thing and write down the correct measurement. All right, let's do the same thing that we just did. So we're going to find the two marks that our measurement falls between. So that's this one and this one. So the first one's 4.5, the second one's 4.6. So I'm going to write down 4.5. And then I need to estimate the next one digit. And so it's kind of halfway between, so I'm going to just go with 5. All right, we've got our results down. Let's look at them both side by side. And you'll notice that on the left here, we only got 1 decimal place, right? But on the right, we got 2. And so the number of marks on the tool that you are using tells you how many digits you need to write down. So you can be very precise if you have a tool that has enough marks for you to get those numbers. However, our eyes are only so good. So using tools like rulers or balances or graduated cylinders or other glassware that has lines on it that you fill to a volume, those are all examples of things that will follow this strategy. Should you round up? You should not need to round at all because you are just estimating the next number. So I wrote 4.55 because I thought that it was halfway between the two marks. So if you think it's a little further than halfway, you could put 6. If you think it's not quite halfway, you could put 4. But that number you just treat as is. You don't need to round it at all. All right, that's our strategy for how to measure something, okay? So make sure you're following that technique for everything that you do that involves a tool that you use to measure. Now, when I report this number to you, I'm not telling you anything about the tool that was used. For example, if I just tell you, oh, the object I measured was 11.64 centimeters. So this could be like, I'm trying to think of something that would be that long. Like in the medical, I'm like fingers or something. I don't know. And so if I tell you that number, it doesn't tell me anything about the tool that was used. What we had to do is infer that. So we would know that, oh, okay, so here are where the marks went. They went every 0.1. And then that this last number was estimated. Okay? So we can work backwards to use the number that is given to determine what was the device that we used to make this measurement working like. The other thing that we can do is we can determine how good of a number it is by how many digits there are. How many significant figures are in our measurement. And so what that means is how many digits were you able to write down? More digits is better. So counting the number of digits will tell us how precise our results are. Since this number had 4 digits in it, we could say, oh, it has 4 significant figures. I wrote a 1, a 6, and a 4 to get the value of my object. Now, sig figs are any digits that you know for sure because the device told you to, or that you've closely estimated, so that last digit counts as a sig fig. It is not just a randomly assigned number. We put that 4 there because we thought it was about 4/10 of the way through between 11.6 and 11.7. Now, if I had a better tool like this, and I got this as my measurement, you could imagine that there would be really, really, really tiny marks all the way down to this position, and that this 5 would be estimated. Because that's how numbers are written. The last digit is the estimated number. All the other numbers are known based on the device or tool that you were looking at. The other way that we would know that this is a more precise number is because there are 9 digits that are written there. If I know very, 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 very precisely about this specific measurement, I can write down that many more digits. So our goal becomes twofold here. One, write down the correct measurement for an object using a different scale, such as a ruler or graduated cylinder. And then once you have that, determine the number of sig figs. Or, working backwards, take a number with sig figs and learn about the tool that was used to make it. That's going to depend on what application you are using and what a problem... Oh, excuse me. What a problem is asking you to do. All right, so let's do that. Let's work backwards. I'm going to give you this number. I made a measurement and I got 540. Which graduated cylinder did I use to record the number 540? Tube A, or cylinder A, B, or C? Now, if you aren't sure, work forwards. Write down the correct amount that each graduated cylinder would contain. Just a heads up, these all start at 0. This one actually doesn't. It's just zoomed in of this part right here. And for some reason, there's an extra line here. You should ignore that. Okay. So write in the chat which graduated cylinder you think delivered 540. And then I'm going to show you how to get all of the numbers and make that assessment. All right, everybody leapt on cylinder B. It has to be cylinder B, right? And the answer is it's totally B. Just kidding, it's not C. It's totally B. Let's write down what the measurements are for each of these. So for this first one, there's actually a little bit of confusion here. They're like, what mark do I write down? Well, I write the lower of the two marks. So do I write 0? And then guess the next digit? And the answer is, no, you totally don't do this. Now, I'm going to show you a different graduated cylinder for A so you can see what happens in this circumstance. So I'm going to write 1,000, 2,000, 3,000. And let's suppose that my object fell here. Well, you would write 2,000, and then you'd guess the next digit, which would be this, right? So you'd guess in the hundreds place what this was. And you'd write down like 2,500 or something, right? You could not write down this point whatever, because that would be something right here, right? And that's not what this number is, so we want to have something that preserves the value. Now, I could do the same thing right here. If this was what I wrote down, this would be about, I would write 1,000, and then I'd guess the next number, which I'd say is like 6 or something. Okay, well, if this is my graduated cylinder down here, what happens if this is my measurement? Do the rules just suddenly fall apart? And the answer is, well, no. Instead of guessing 2,000 or 1,000, these all go to the thousands place, right? I'm going to guess 0,000 because that's the lower mark. And then I'll estimate what this is. It's about 600, right? And then nobody writes numbers like this, so you just get rid of this first 0. So that first number, in fact, the only number that we've written here that has any value, this is our estimated number. And our known numbers are just 0. 0 is a known number, it turns out, if you're using a scale and the first mark is 0. You just need to put the 0 in the correct place so that you get the right number, okay? So what we would say for this graduated cylinder is, since it's in the middle, wow, I totally missed that, but that's okay. I would say that this is 0,500, or just 500. For the rest of these, it's pretty straightforward because we have 2 marks that we can easily identify. I've got 500 and 600. I'm going to guess this one to be 540 because lo and behold, that's the number we're looking for, right? And then for graduated cylinder C, I could write 540 as my first mark, and then I'll guess the next digit, which would be in the ones place. And I'd guess that to be like 543 or something. That sounds good to me. And then finally, these are all in milliliters. So there's our answers. Now something's going to appear right here, so I'm going to just try and clear this. So there we go. Now you can see that the numbers that we wrote down have increasingly more and more sig figs, but there's an issue here. I wrote down 3 digits for all of them, so they all have 3 sig figs? Well, not quite. These zeros here have a very specific purpose, and that purpose is that these zeros are what are known as placeholders. If I estimated the volume of graduated cylinder A to just be 5 milliliters, that wouldn't make much sense because that would be like right here, wouldn't it? Way down at the bottom. I need those zeros to push this 5 into the correct place, the hundreds place. So when you see zeros at the end of a number, and the purpose of those zeros is to just be a placeholder, that zero is not significant. We're not going to count it as one of the sig figs because we don't really know if it's 500 exactly or 500 rounded. We don't have the marks on the device to tell us that. If we had better marks, we could get more information. That's why we can write 540 on the second one. Even though they're all the same height, I should get the same answer every time, right? Well, there aren't enough marks on the one on the left in graduated cylinder A to tell us anything about how much liquid there was in the container if it's just poured in this rough 1 liter jug. All right, so now that we've seen some examples that have zeros in them where we don't count them, let's talk about all the different situations that you have to watch out for zero. Because what you're going to do is, instead of just taking numbers from measurements and interpreting them in reverse, like, oh, okay, which tool measured what or whatever, generally speaking, you're going to just be given a number and asked, how many sig figs does this have? How precise is this number? Now, for any digit that's non-zero, if you are given a value and you see non-zero digits in there, count them as significant. So this number here, I would say, oh, these are all significant, which I'm going to abbreviate as SF, and there are 4 of them. But these depend on the application and the context of the problem that we're looking at. Those zeros might be known, or they might just be placeholders because I was rounding to the thousands place. Which is which? Well, it depends on the context of the problem and how the number is written. So we're going to examine that in more detail. Let's look at the first case where 0 is not a sig fig. And here's what I'm going to do. I'm going to leave that off the screen here. All right. I owe you $3,996. So what I'm going to do is I'm going to round up to 4,000 because that's easier to deal with. And then what I'm going to say is, oh, these zeros aren't significant because they're just 0, right? They don't mean anything. And so I'm going to pay you this much. Are we settled on our debt? Would this be acceptable? No, right? Not just no, but fuck no. That's just insulting, right? Don't be ridiculous. You don't pay $4 on a debt of $3,996. Like, that's absurd. So those zeros must totally have some meaning to them, right? Why do I put the zeros there? Because if 4 by itself is in the ones place, right? Well, I don't owe you 4 ones, I owe you 4 thousands. So what I need to do is add zeros until that 4 is in the right spot. So that's not the right spot. That's not the right spot. That's the right spot. There you go. That's the correct amount I owe you. Now, if these zeros are included in a measurement, these are not sig figs. Because you don't actually know their value. If I rounded $4,000 and I said, this is about how much I owed somebody, I mean, depending on where you rounded to, you could get 4,000 multiple ways, right? Maybe I owe you $3,750, and I just decided, oh, I'm going to round up to 4,000 because I'm sure I will owe you an extra little bit at some point, and this will just take care of that. Or maybe I had 39,000, or not 39,000, $3,999.92, and I said, oh, I'm going to round up to 4,000. We lose all of that information in rounding to one digit. So if you have a one-digit number with a bunch of zeros after it, those zeros are not significant figures. They don't tell you anything. They are just there to make sure that 4 is in the right spot so that I give you the correct magnitude of money. Not $4, but $4,000. Now, when you look at a bunch of numbers and ask yourself, are these placeholders? Am I putting these zeros down so that the magnitude of the number is the correct magnitude? The easy way to do this is to take a pencil or a highlighter or something like that and just draw over all the zeros. Now, obviously, you can't really do this on paper, but if I do this, for example, did I change the value of the number? So before it was 1,250,000, but now it's 125. Did I change its value? I did, because 125 is way too small for this number, right? If I owed you $1,250,000 and I paid you 125, you'd be very upset. What about this? I have this crazy decimal here, 0.000004386. That's a really, really tiny number, right? Well, if I get rid of these zeros, now it's a fairly large number. That doesn't make any sense, right? So those zeros must be placeholders. They are to make sure that my 4,000 is in the correct magnitude. And it should be a really small number. So the zeros that are shown on the screen are placeholders and don't count towards sig figs. Because we don't know what their value is. All we know is we have to include them so that we get other numbers into the correct magnitude. All right. So again, try to apply that strategy while you're doing these types of problems. Does the number of zeros change, or does covering up the zeros change the value and the magnitude of the number? If yes, those zeros are placeholders. They're not, they're not significant. Now, if you have zeros that appear between two sig figs, those zeros are significant just based on where the scale lands. So here are all these sig figs right here. And I have this zero trapped in the middle. If you see zeros between other digits, they are also sig figs. So this would have 7 because there are 1, 2, 3, 4, 5, 6, 7 digits. 6 of them are non-zero, so they always count. They're known. And then that other 0 there, we count it too because it's also known. For example, if I'm counting by ones and I go 998, 999, 1,000, 1001, I know all of these digits for sure. And then when I get here, I still know these, and I still know these up here too. Now, we're going to show how to represent this, because as written, this would be like, oh, there's only one sig fig here. How do I make it be 4? We're going to figure that out in just a little bit. Also, every time I give this question, I mean, this is one of the first jokes I put in my slides here. Anybody know what that number is? Try saying it out loud. And then during the break, you can go find this. Let me see if I can find it on YouTube here. Yeah, here we go. I can't actually play this on YouTube because I'll get a copyright strike, but this is an old classic song from forever ago. 1982, it says, which was 1 year before I was born. So there you go. 8675309. All right. The last rule that we're going to deal with for figuring out sig figs is called the decimal rule. Now, the decimal rule must be applied if you have a decimal. So if you see a decimal point, you have to use this rule. Okay, it's not optional. You have to do it. So here's the decimal rule. Step 1, find the decimal point. There it is. If you see it, we have to do this. Step 2 is underline anything that's not a 0. There you go. Finally, step 3 is whenever you see the decimal point, anything that is to the right of your underlined digits is a sig fig. Anything that's to the left is not a sig fig. So on the left, we have the placeholders. But on the right, we have sig figs, and they do count. Why would these count? Well, this is a situation for when you're measuring something where you land exactly on a line. For example, if this was my graduated cylinder and it landed right here, and I had lines that were going like this, so do. And so you could see here that we're counting by ones, right? So if I was going to write down the next 2 marks, the first mark I would write down would be 100. But in order to represent that ones place is known, I have to put a decimal there. And then I would guess the next digit, which would be that. Okay? Now, there's a bunch of zeros here. If I get rid of this 0, it's still 100, right? It doesn't change the value, but why would I write that 0 here? Well, I'm writing it because it's known. I have estimated that the next digit is 0. So I want to keep it. If I wanted to estimate that the next digit wasn't 0, I would have to have my liquid not fall right on that line. So this could also be written as 100, right? It was like right here. But then the next digit I estimate would be like 0.4 or something. So there will be circumstances where you just happen to land on a 0. And when you land on a 0, the decimal rule takes care of you. Okay? Now, what that means is that you can get some really obnoxious circumstances where if I say 200, this is written as 1 sig fig, but if I put a dot in there, now it's 3. So be careful when you see the dot, okay? Make sure that you're applying the decimal rule. The position of the dot does not mean anything. The only thing you're going to do is, okay, underline the non-zeros, and then everything to the right also counts. There's some examples on the board there. Those are not negative symbols. Those are just tabs. So what I want you to do is, I'll put the homework on the board here. I want you to do these practice problems. I want you to count each of these as a measured number. So assume that some sort of tool was used to measure these. None of these are counted. I mean, if you play Dungeons and Dragons, you know that XP is counted, but just assume that these are numbers that you measured on like a ruler. Tell me the number of significant figures in each number as written. Okay. Write your answers in the chat, and we'll go over them together in just a second, and then we'll take our break. One more minute, we'll go over the answers. Alright, so what do we got here? So I got the number 900. Oh, I need a color that we can see. Let's do blue. Alright. I have the number 900 here. I've got a digit, so this counts. But these other zeros are placeholders, so there is only one sig fig. Because if I were to scribble these out, the value of it changes. 9 and 900 are not the same number. Same thing with 90210 here. So if I scribble out this 0 at the end, the value changes, and there's no decimal point to save it. But these other digits that are non-zero, so this one, and this one, these all count. And then the 0 right here also counts because it is trapped between two sig figs, so we count it as well. I use the abbreviation SF for sig figs. You might see that other people do that too. For the mass of a flea here, we got the decimal rule, so we got to do this. So underline the non-zero ones, so those count. And then everything to the right counts too. Everything to the left is a placeholder. And you can see that here. If I cross this out, now the number is 870. That's way too big, right? If you had a flea that weighed 870 grams, that's like a cockroach at that point. That's just gross. Ugh. And then finally, 500 milliliters. Oh, there's a decimal, so we have to follow the decimal rule. So we got this number, which counts, and then everything to the right counts too. So this also is 3 sig figs. All right, looks like everybody did pretty good there. So there's the homework practice. The first 40 problems in the homework set in the text deal with counting sig figs and answering questions about sig figs, and I recommend doing all of those for sure. All right, we are due for our break because we're at the top of the hour. Well, the hour for class. It's the middle of the hour. That's where we start. So let me put this on the screen here. I need my timer. Where is it? There it is. All right. And then I'll see you in about 10 minutes here, following some more Bravely Default. Hello, welcome back. Yay, we landed right on 10. Hooray! That doesn't happen very often. Alright, let me wind the music down here. Alright, it's time to do math. Now that we've learned how to do sig figs, there's kind of an important consideration that a lot of people don't want to make, and that is that the topic we just covered, what sig figs are and how to count them and some stuff like that. It's not a curiosity. This is not something that you're going to be like, oh, that's cool, and then just go back to whatever you're doing. No, whenever you use numbers in this science class or any other, you need to apply the rules of sig figs, because the whole point in doing the discussion about sig figs is to talk about introducing error. And in some measurements, you can have some error. It's okay. If you give a child 50 milligrams of medication, but you measure out 49.7 or 50.2, you're probably okay. But for some things, like the amount of lead that's allowed in water, if the amount of lead that's allowed is 6 parts per billion and you expose somebody to 8, like, that's a 50% difference, even though the number is really tiny. And so we need to be considerate about what these errors mean and how they would influence our calculations. So we are going to consider sig figs in everything we do. Don't just hit flush and dump this knowledge out of your brain now that we've gone past the significant figures chapter. So we're going to learn how to do math using significant figures, which means basically everything you know about addition and multiplication is wrong. So let's learn again. On the board are 2 easy problems. Everyone in this class can do these problems. I am 100% confident in that. But not everybody probably knows how to deal with significant figures in these problems and what the correct scientific answer is. So we're going to work through the addition problem and the multiplication problem and show how to get those calculations for each type of problem. Now, something to note, these are 2 different problems that will have 2 different strategies. There is an addition and a subtraction strategy. And the strategy is the same for addition and subtraction. And then there is a multiplication division strategy. And these are different strategies. Okay, so be careful. Don't apply the rules from one thing to the other. Don't just do the addition rules to everything when you learn it, because it's the first thing you learn. Don't just apply the multiplication rules to everything because it's easier, okay? These are separate rules. Make sure that you are applying them to the correct instance. So here we go. If you were going to add these numbers traditionally, what you would do is you would say, okay, if I have a blank here, I'm going to just treat it as a 0, and I'm going to just add straight down. So 0, 1, and 0 becomes 1. 8 and 4 is 12. We'll carry the 1. 9, 15, 19. 1, 2, 3, 12, 15. Carry the 1. I don't know why I made this carry so many 1s here. 13, 5. So this is the number that you'd get if you did the addition in 2nd grade or whenever you learned how to do this, right? Everyone can do that. But if all of these numbers are measured, then what that means is that the tool I used to get this first number, for example, had marks on 352 and 353. That was supposed to be a 3. Wow, I don't know how to numbers today. Hold on. I want to blame PowerPoint or my pen, but I think it's really just operator error here. All right. So the number 352.8 is implied by this measurement right here. And my object probably was like that, right along the middle of that. So following the measuring rules, I said, okay, well, I'm going to write down the smaller mark and guess the next digit. And so that's the number I wrote down, was this number right here. But I can't get these next 2 digits here. I don't know what these are. In fact, based on this measurement, they could be literally any number. To guess that they were exactly 0 is misleading. So I can't assume that 1 plus blank equals 1 if these are question marks and these blanks. So I'm going to put those down right now. 1 plus question mark is not 1. Instead, it is question mark. So I don't get to know this number. It's a question mark. Same thing here. 8 plus 4 plus question mark is not 12. It could be any number it wants to be, so this becomes a question mark too. But right here, I reliably know that 8 plus 6 plus 4 would give me something that is approximately the digit I wrote here. Now, I got an 8 if I do the addition here, but carried over from the numbers that we know, it would round up to 9. So the correct answer we would write would actually be this. And I don't get to keep these 2 digits over here because they were mucked up by question marks. And so the strategy for addition is pretty simple. Add vertically like you would normally do, treating the blanks as 0, then fill them in with question marks and just chop off anything that's a question mark. You don't get to keep it. Now, we have a formal way to do that, but that's the gist of it, is you're going to just drop all of the numbers that question marks had an influence in. Here's the algorithm for how you can do that. So first we're going to do the math here. I'm going to write in the number here. So this was the number that we got when we did the addition. Then what we're going to do is, let me uncircle that real quick. Here are my question marks. And I'm going to look for the most precise place. What that means is the number that is furthest to the right, that there is a digit in every value. So I'm going to start up here. I'm going to do the rightmost column. Is there a digit in every value? No, there's question marks here and here, so I don't get to keep that number. Let's look at this one. Is there a digit in every value? No. Let's move over. Is there a digit in every value? Yes. So I get to stop at that spot, but no further. I cannot keep anything past it. That's how we circled that spot. Oops, I erased everything. So there's our number. That's our answer we report. So again, work from right to left. This is the most precise, because the thousands place is very precise, but the hundreds place is the least precise. And just work right to left. So, oh, there's stuff here, so no. Oh, there's a blank here. No. Hey, this one's good. We round here. Now, this is easy enough to do with decimals. If you have a bunch of numbers with a bunch of decimals, you can do this no problem. Let's do another example with decimals involved, and then we're going to start using numbers that aren't decimals. And you'll see that it gets a little bit, it's not hard, but it's strange. It's a little messy. I got to just do it this way. All right, so we'll set this up. 4.83 minus 0.7. Now, subtraction and addition follow the exact same rule. So we'll just treat it like it was addition, except we'll follow the subtraction rule. So 3 minus blank is 3. 8 minus blank is 1. Or I'm sorry, 8 minus 7 is 1. 4 minus 0 is 4. There we go. And then we're going to do the same thing. Let's look at the most precise place. That's this one. Is there a digit in every value? Well, no, there's a blank here, right? So I can't use this. I can't use that position. Let's look over here. Yeah, there is a value in every number, so I'm going to round to that. So I should round my answer to 4.1. That would be my answer for this problem. All right, so let's do another one here. We'll just leave space for the answer to pop up when I hit the button. Let's add 7,300 to 139.228. So 7,300, 139.228. All right, we'll do the addition here. So these numbers get carried down. 9, 3, 4, 7. All right, now I gotta do the same thing. Now, obviously, if I'm starting over here, these are all blank, right? So I'm not going to get to keep any of these numbers. But what happens when I get here? Is this 0 known or estimated, or is it a placeholder? If it's a placeholder, then it's effectively a question mark, because that number could be like 7,268, right? But rounded to this spot right here, it would round to 7,300. So this blank right here, this 0 right here is a placeholder. This could be any number it wants to be because it's a placeholder. So we can't count it either. And so we can't use that spot either. Nor can we use this spot because it's a placeholder. This is the first position where I have a digit in every spot. And so I would round my number to this result. And so the answer I would not write 74 because that would be the I owe you $3,996. I'm going to round it to 4,000 and pay 4. We need to put zeros to get the correct magnitude. So I would have 7,400. And this would be the result that I report. All right, that's a little weird. But we are following all the same rules. Let's do another problem that's very strange here. And see what we get. So what is 3,000 plus 6? And you're probably going, it's 3,006, but we have to apply the rules for sig figs, right? And remember, there's the numbers I know. These are all placeholders, and so I don't get to use this spot, or this spot, or this spot. In fact, the first position that a number appears in every value. Remember that there are invisible zeros here, and these are all known. The first spot that actually has a digit that is known for every value is the thousands place. So I need to round to this spot, and this would be the number I report. So in this class, 3,000 plus 6 is 3,000. And you're probably sitting there like, what the hell? That doesn't make any sense at all. Where the hell did the 6 go? Is it just gone? Yeah, it's gone. Now, it turns out that this is actually really easy to explain. And it has to do with the issue of magnitude. So here I have a number in the thousands place. And here I have a number in the ones place. And these are very far apart. Let's do an analogy and see if we can explain this in a little more detail. Let's suppose that you won the lottery, you win Mega Millions or Powerball or whatever it is for Washington. I think it's Mega Millions here. And you win $696 million. Now, you celebrate in the only way you know how, because you're new to this millionaire thing. You go out and buy a cheeseburger for $6.99. How much money do you have left? Is it $695,999,993? Or do you just say, I don't give a shit about these digits anymore. I have $696 million. You don't care about the digits in the ones place or the tens place anymore. Shit, you could drop $10,000 and these digits don't even flinch, right? You have $696 million. That's not just walking around money. That's all the money you could ever imagine. And so you could spend amounts of money in these digits, and these numbers up here go, I don't care. Doesn't matter to me. Go ahead and drop $100,000 on that sports car that you really want. Yeah, you still have $696 million, rounded to the millions place, right? So if you have numbers that are really far apart in magnitude, you get odd results like this where the next number doesn't change the first number. We can show that even in a picture. So let's suppose that you have like a jelly bean factory, and the jelly beans are measured, and I'm not going to draw all these jelly beans in here, but there's my thing. And they're measured in like the tens of thousands. Oops. I want to have more marks than that. So this will say this is 10,000, 20,000, 30,000, 40,000. All right. So there is some number of jelly beans in here. And so we would estimate that this would be, using this measuring scale, about this many. Now, it's a late shift for you. You no longer have $696 million. You are now an employee at the jelly bean factory. And so you sneak in to the jelly bean pit and you eat a handful. Boop. There you go. You ate a handful. Maybe it was like 16 jelly beans or something. I don't know how many jelly beans you can eat at once, but that sounds like a lot to me. How many jelly beans are left in the bin? Nobody gives a shit, right? Because you have pretty much the same amount as before. Your indentation did not affect the result in a reasonable way. And that's how sig figs work, right? Because are there exactly 22,000 jelly beans in this bin? No, there could be any number. Is 16 going to affect that number? No. So this is why you get weird results when we do certain types of problems, and it has to do with how orders of magnitude work in measurements. If I estimate that there are 22,000 jelly beans in here, I'm still going to estimate 22,000 whether or not you stuck your face in it and went chomp, chomp, chomp for 20 seconds, right? It's about the same number. There's no way you could eat that many jelly beans. Don't kid yourself, even if they're delicious. You just can't eat them that fast. All right. So that's how addition works. And subtraction too, because they're the same rule. We're going to just apply the rules for addition and subtraction by setting everything up vertically, doing the addition, and then finding the first place, working from the right to left, where everything shares a digit that is a significant figure. Placeholders or blanks in our decimals, can't use those. Cross that whole position out. Go to the next one. All right. That's how we do addition and subtraction. What I want you to do is now like hit save, Control S, or new piece of paper, draw a really thick line, and then we're going to do the multiplication rules because the multiplication rules are different. Okay? Be mindful of this difference because if you apply the addition rules to this, they don't work. Now, the premise is sort of similar because when you do a multiplication, if you do long multiplication, for example, let me write this number down. What you are doing is you're multiplying numbers. You'll get a bunch of numbers here. And then remember that you like put placeholders here, so you'd like put a 0 and then a 0, 0 or whatever, or X's or something like that. And then at the very end of this, you do addition and do all that. This is what your 4th grade kids are doing in their math class, and then you have to help them, and then you're like, shit, how do I do this again? Well, now you're learning it in Chem 121, so you can help them again. I mean, I'm not going to do the long multiplication because we have a calculator for that, right? But if I were to do this multiplication, I would say, okay, 5 times 4 is 20. 8 times 4 is 32, plus 2 is 34, and so on and so forth, right? But what do I have these question marks here for? Well, if I put enough question marks so that everything goes to the same number of decimal places, I'm going to start getting question marks in my result, aren't I? So when I do the long multiplication, there's going to be a bunch of question marks in here. And then suddenly I'll start having actual numbers in here when I do the addition. And so I will get a bunch of places that get crossed out when using the addition rule. Now, fortunately, somebody has made this a lot simpler, so we don't have to worry about doing the long multiplication every time, because that's super tedious. So what we're going to do is we're going to do the multiplication and just write down what the calculator says first. And then we're going to look at the numbers that went into this measurement. The first number was using a very, very precise tool. The second number is using a really, really bad ruler. Now, if I have a measurement that was great, and I have a measurement that was bad, and I try and do math with these two numbers, the result will be only as good as the worst step. A good analogy for this would be cooking. If you're going to make, like, say, chicken enchiladas. I made chicken enchiladas last night. They were fantastic. I can't wait to eat those. But let's suppose that I put the chicken in, and I fry up the tortillas, and I put the onions in, and I put all the seasoning in, and then I top it with moldy cheese. And I use all the cheese, and it's all moldy. It's totally green and gross. What will my enchiladas taste like? Well, considering that I just covered them in moldy cheese, my enchiladas will taste like mold, right? So it doesn't matter how many great ingredients you have, you put in one single poor one, and everything tastes like shit, right? Don't do that with cooking. Make sure that when you're cooking, you're using only good ingredients. The best quality that you have available, right? Don't just be like, well, if all the ingredients are good, who cares if the chicken is past expiration? Everything else will be great. They'll just cover it up. No, you'll get salmonella and you'll regret everything, right? Don't do it. Use good ingredients. With measurements, it's the same thing. If you use shitty numbers, you get a shitty result. And the way that we're going to represent that is by counting the number of sig figs that are available to us in each measurement. This number has 1, 2, 3, 4, 5, 6 digits available to it. So I'm going to say, okay, it is 6 significant figures. This number, however, only has 2 significant figures. It's the crappier of the two numbers, and it's going to be the one that affects our calculation. So when we're done, our answer will have whichever of these is the smaller number of sig figs. So I will get a number, and then I will have to round it down to this many sig figs. That will be my result, because 2 is smaller than 6. If I knew these numbers, I could get it up to 5, and then I would round to 5 sig figs for my answer. But I don't, so I only get to have 2. All right, so let's punch this in the calculator. If you have a calculator, you can do this along with me. And you type in 14.2985 times 6.4. And my calculator spit out this, 91.5104. That's what I wrote here. But I'm only allowed to keep 2 sig figs, and they need to have a magnitude close to this number. Because this is what the calculator said. 14 something times 6 something is about 91. So I can't just keep this, because if I wrote this is my answer, that doesn't make any sense. Right? 14 times 6 is not 4. So I need to pick 2 sig figs, and they got to start from the left. So I'm going to pick these 2 sig figs. And so then I would round to this position, which would be the ones place. So 91.5104 would round in the ones place to 92. Why 92? Because we ended on a 5 or higher, so we'll round up. We're only going to do standard rounding in this class when we do this. So don't do bankers rounding, don't round to even, don't round to odd. Just 5 or higher, round up, 4 or lower, round down. So the number I would report here is 92. All right, let's do some more examples here. And you can type in the answer if you get these before I do. Oops. Actually, I don't even need this sheet because I'm just going to be punching stuff into the calculator. So we'll just go back over here. So I'm going to type these numbers in the calculator, but the first thing I want to do is I want to count the number of sig figs. So this is 5 sig figs, and this is 2 sig figs. So my answer should have 2 sig figs. So whatever I get on the calculator, I'm going to round it to 2 sig figs. So 5.4336 times 1.2. I got 6.52032. I got to round that to 2 sig figs, so I'm going to take the first 2. There you go, 6.5. Very good. Let's do another one. What is this? I'm writing a little slash mark because I can't typeset a division character in the font that I was using, nor do I have like a formula editor in PowerPoint available for me. So we're going to do the same thing. This is 5 sig figs. This one has, okay, it's a decimal, so we got to do these two. This one counts, so those are my sig figs. That would be 3. 3 is less than 5, so my answer has 3 sig figs. And then I would punch it in the calculator. 34.836 divided by 0.380. And I get 91.67368,421. My answer should have 3 sig figs, so I'm going to keep these 3 and then round. All right, let's do the last one. What if I do this calculation? Well, here I have a number that's really precise because there's 6 sig figs. But here I have a number that's just 1 sig fig. So when I do this division, I'm only going to get to keep 1 sig fig, which means I'm going to have to do a lot of rounding, right? So 7.63829 divided by 2, my calculator says 3.819145. But I only get to keep 1 sig fig, so I have to round this to 4. Which I know, it sounds totally obnoxious that we have to do that much rounding. But based on the number 2 there that we used, that 2 is not very precise at all, and it ruins our accuracy. Alright, sounds like you got the hang of it. So now, the last thing we have to do is answer... Well, we have to answer one question, but there is a little caveat. If you're using your calculator, and you're doing addition, or multiplication, this is common with addition, but sometimes multiplication will do this too. Your calculator doesn't know what sig figs are. So if you type this calculation in your calculator, you're going to get an interesting result. But when you do it by hand, it doesn't match what the calculator says. So if I do this addition by hand, this is what I get, 0008. And then when I check for sig figs, I have a digit in every position in the thousands place, so I get to keep all these numbers. So this is the correct answer. But what your calculator will show is it just prints this. And that's wrong. Your calculator did not include the correct number of sig figs, okay? So be very careful when doing a calculation on your calculator, because Wolfram Alpha does this, your TI-83 does this, all sorts of calculators do this, and you need to be mindful that you need to go and fill in the sig figs. So if I need to go to the thousands place, because that's the first spot that had a number in it on all of these, I need to manually fill in those zeros if I do this calculation on a calculator. So be aware that calculators are not the answer. You cannot just plug a number into your calculator and expect the correct answer to come out. You do have to use these algorithms, okay? So you do have to learn them. You can't just say, oh, well, this is easy. The internet's going to know how to do it. No, the internet will do this wrong for you. Make sure you are doing this correctly using the algorithms we just talked about. All right. Last thing to cover. What happens if you have to do both things at once? This is where people get confused. They say, well, what rules do I have to use? Like, what do I do? Can I just do the multiplication rule? There's 3 sig figs, right? Hey, this is the smallest one, so my answer should have 3, right? Totally wrong. Don't do that, okay? Here's what you need to do. First thing you need to do is use order of operations to figure out what operation you're doing first. Everybody remembers their order of operations, right? We all remember PEMDAS, right? Remember the algorithm? Please excuse my dumb ass sibling. Right? That's the way you all learned it, right? Maybe not, right? But anyway, that was parentheses, exponent, multiplication, and division. Let me not write the multiplication like that. But multiplication, division, and then addition, subtraction, right? That's the hierarchy. We got to do the parentheses first, then any exponents, then we do multiplication and division, and then we do addition and subtraction. So what do we see on this that we have to do first? Well, there's parentheses, so we're going to do what's in the parentheses first. So let's do that. So if I do subtraction for what's in the parentheses, first I'll just do the subtraction. We'll subtract vertically. So 73.8 minus 70.983. And my calculator spits out this, 2.817. Then we'll do sig figs for that subtraction. So basically, we're going to do this stepwise if we have to. And so if I do this, I'll go, okay, well, there's a question mark here and there's a question mark here, so I don't get to keep these digits. This is the result of the subtraction. So this top part is 2.8. Now that I've done the parentheses, I can then do the division. And we'll do that. So now I have 2.8 divided by 2.639, which I'll then round to 2 sig figs because this is division. This is the smaller, so my result will have 2 sig figs. And I get 1.1 as the answer. So whenever you change whenever you change operations, you have to apply the appropriate rule. Make sure that you are applying the rules correctly and doing your sig figs before you go on to the next number. Now, if you aren't changing operations, you can do all the operations together. For example, if all you are doing is multiplying, multiply all the numbers together, pick the one that has the fewest sig figs, and then round your answer at the end. If all you're doing is addition or subtraction, add all the numbers together vertically and just do all the sig figs at once. But if you have to change between these two operations, between multiplication and then addition, then every time you have to change operations, you have to stop and resolve your sig figs before you move on. Okay? All right. You now know the rules. We've done a few examples, and you can always flip back through the video if you need to. Now you have to actually do the problems. Okay? And this is actually rather challenging, so I'm going to have you do them. We're going to go over all these answers together at the end. All right. So I want you to do these 7 calculations and report your answer to the correct number of sig figs. Typing it in your calculator is not enough. You will not get the correct answer. In fact, I have programmed the problems for this section in for Canvas that if you type in this, you might have seen this meme around where somebody types in the answer 15 and Canvas goes, nope, the correct answer was 15.0. And the student was like, ugh, that is stupid. This is that problem. And yes, this will be marked wrong if this is the correct answer. Okay? So be very careful that you're following these rules. Good luck, and I'll check in with you in just a second. About 2 or 3 more minutes, and we'll go over the answers together. All right, let's go over the answers here. I need to get into this screen, and let me get rid of all of that. There we go. All right, so the first thing we want to do for this first problem is actually for the multiplication and division ones. I'll just write on this screen real quick. I'm going to multiply these numbers together in the calculator. So 0.0019 times 21.39. And the answer that it gives me is 0.040641. But we also need to worry about sig figs. So this first number is 2 sig figs. This one is 4 sig figs. So our answer can only have 2 sig figs. And so that's going to be, well, if I kept this, my answer would just be 0, right? Those are placeholders, so we don't keep them. We just include them, and we go over to that, and those would be the numbers that I keep. We'll round up. So 0.041 is my answer. Gotta have 2 sig figs. For the second one, I do the same thing. I'm doing division. I'm going to just punch it in the calculator. The number that I get is 2.029512195. I'm not going to keep all those digits. I'm going to only keep, well, this is 4 sig figs and this is 2 sig figs. So I will keep those 2. So I'd report 2.0 as my answer. All right, for the third one, I have to do addition. Let me put those on the screen here. And we'll just scroll up so that I have more space to work with. There we go. So we're going to do 3,020.3. Got to line them up so the decimal point's in the same spot for all of them. 009. And when I add all these together, so we'll do it normally. There we go. But now we got to start looking for where there are blanks. So there are lots of blanks in here. So none of these numbers get to come along with. But these zeros right here, these are all placeholders, so they don't get to work too. So I don't get this one or this one or this one. This is the first spot I get. So I would report 3,000 as the answer for the third problem. So I'll go write that in really quickly. All right, for the last, or this problem, let's see here. So we got 4.33 minus 3.62. We'll do the subtraction. 13 minus 6 is 7. 3 minus 3 is 0. And then I will look from right to left. So we'll look here. Oh, there's a digit in all of those, so I get to keep the whole thing. So this is just the answer to your report. Notice that there are fewer sig figs than you started with. So you can start with 3 and then end up with 2. That's totally allowed in subtraction. Subtraction does not care about sig figs. It cares about places, and places only. All right. This next one's just a concept chapter. We all know that 6 times 2 is 12, but what's 6.000 times 2.000? Well, you punch in your calculator, it just spits out 12, right? Well, what the deuce? What am I supposed to do with that? Well, you follow the rules. How many sig figs does this have? 4. How many does this have? 4. Okay. I multiply them together, and my answer has to have 4. So I need to go like this, so that it has 4 sig figs. If you just write 12, that's too few sig figs. And if you wrote 12.000, because everything else had 3 zeros, that's too many sig figs. So be careful. For the next problem, we're going to do the addition first, and then we'll do the multiplication. So let's do the addition real quick. Oops, hold on. Wrong color. 4.281, 37.3. We'll add these together. I believe that that's right. I was adding the wrong direction. And then can't use this because there's nothing there. Can't use this. Here's the first spot we round to. So I would report this value as 41.6, which we can then put in the calculation up here. So this is 41.6 here. I will then multiply it by 0.00390. Both of those numbers have 3 sig figs, so my answer should have 3 sig figs. And the answer I got was 0.162. And then finally, for the last problem, I need to do 52.5000 divided by 3.6. Well, this number as written has 6 sig figs. This number is 2 sig figs, so Whatever my result is in the calculator can only have 2 sig figs. And I got 14.58333, which I have to round to 2 sig figs. That's supposed to say 2 sig figs, so I'll just get rid of that. And then now I do the subtraction here, 15 minus 11, which I'm just going to do over here. And there's my answer. All right, so I see some errors in the calculations. Make sure that you are following the rules for these types of problems. Let me know if you have any questions, but that is all the time that we have today. I did go over by 4 minutes, so I do need to sign out pretty quickly because I have another class that's going on. Can you see all the answers? Yeah, let me put these on the screen. Oops, sorry, there we go. There's all the answers at once. You could pause the video now, but I do have to take the video down, or not take the video down. I do have to end the stream. So yeah, just hit pause, and this will stay available until you unpause it. I do want to thank everybody for coming to the lecture. I said that we were going to do a little bit about the lab today, but we didn't actually get as far as I thought we would. So when's the next day that we have this class? Wednesday? On Wednesday, we're going to learn how to convert between units, and then we'll talk about the lab then. So we'll do that later on. If you'd like to start trying the lab, you can still read through it and do a few of the problems, but the bulk of it we'll do on Wednesday. So we'll take care of that then. Have a wonderful rest of your day, enjoy your Tuesday off, and go out and enjoy the spring weather. See you on Wednesday.